Hello students. Now we talk about the analytical treatment for finding out the resultant for the addition of vectors, and for that we will start with the same figure that we draw for the triangular law. So we have two vectors a and b here, which are added up to give a resultant vector r. Yeah. Now we shall use a little bit of trigonometry and geometry of this figure to find out our resultant vector r if we know the vectors a and b and the angle that they make with each other. Now I shall take this up in a while. How do we find out the angle made by the two angles with each other? For now we will just consider this angle theta, let us say, by extending the vector a horizontally in the same direction and then dropping a perpendicular from the point q, which is the head of b, to see where it meets this extended line down. So this is a 90-degree angle, and let us call this point as S. So the objective of the upcoming exercise would be to be able to find out the magnitude of our resultant vector r as well as its direction, which will completely specify the vector r. When we know the magnitudes of our two original vectors a and b and the angle that they make with each other, which we are here calling as the angle theta. Okay. So understand a few things first, that the vector a, which we can also write as the vector OP, they are the same vectors, and if I talk about the magnitude of vector a, it will be the same as the magnitude of vector OP, which will be nothing but the length OP or the magnitude of vector a. I can write it like this also. Yes, we have discussed this in the previous video, that this is how we can express the magnitude of a vector. Similarly, vector b, which in this figure is also the vector PQ, if we try to take the magnitude of vector b, that will be nothing but the magnitude of vector PQ, which we can also write as just b without the vector sign over it. And the same thing goes for vector r as well. Vector r, which is equal to the vector OQ, when we try to find out the magnitude of it, which is also the magnitude of the vector OQ, will be nothing but the length OQ, which we can also write as simply r. Yes. Now, if we look at this figure and we start with the triangle, let us say PQS, the smaller right angle triangle that we see here, we know that from the definition of sine of the angle, sine theta, which is opposite by the hypotenuse. Here in this triangle, the opposite is QS and the hypotenuse is the length PQ. PQ here can also be written as the vector b, magnitude of vector b. So I can simply write it as b also. So from this expression we can write QS is equal to b sine theta. If we just take b on the other side of the equality sign, this is how QS can be written. Similarly, in the same triangle we can also write cos theta is equal to the base, which in this case is PS, by the hypotenuse PQ, which can also be written as PS by PQ is once again vector b. So from this expression we can write PS is equal to b cos theta. So we are going to use these two equations, call them equation number 1 and 2, into now we take a bigger triangle, the triangle OQS. In triangle OQS, the bigger right angle triangle that we have, see that here we can write the magnitude of the length OQ squared is equal to QS squared plus OS squared. This comes from the Pythagoras theorem, right? OQ, understand, is nothing but the magnitude of vector r, so we can write it as r squared. It is equal to QS, from equation number 1 we know can be written as b sine theta whole square of this, plus OS. See that OS can be written as OP plus PS. So this can be written as OP plus PS whole squared, where we know that OP is nothing but the magnitude of vector A, so this can be written as A, and PS we have just now calculated from equation number 2, it is nothing but B cos theta. So, we can rewrite for R squared, it is B squared sin squared theta plus OP which is A plus PS which is B cos theta whole squared, and now we can open up this bracket. This will become B squared sin squared theta plus, when we open this bracket we will get A squared plus B squared cos squared theta plus 2AB cos theta. Here we have used the formula A plus B whole squared is equal to A squared plus B squared plus 2AB cos 2AB. Yeah. Now, if we look at these two terms, B squared sin squared theta plus B squared cos squared theta can be brought together. I will first write A squared here, and then we shall take B squared out of these two terms, where we will be left with sin squared theta plus cos squared theta inside the bracket plus 2AB cos theta. And we know that sin squared theta plus cos squared theta is 1. So, this will give us R squared is equal to A squared plus B squared plus 2AB cos theta as our final expression, which we can also write as R is equal to square root of A squared plus B squared plus 2AB cos theta. So, this is our final expression for the magnitude of the resultant vector R. This is the magnitude of the resultant vector R. See that the magnitude of R does not just depend upon the magnitude of vectors A and B, it also depends upon the angle between the two. So, if we take two vectors having a certain magnitude, and if we keep on changing the angle between those two vectors, the resultant will take different values then. Yes, this is what we understand from this expression. So, this gives us the magnitude of vector R, but that does not specify vector R completely. Since R is a vector, in order to completely specify it, we should be able to find out its direction also. Now, how do we find out the direction of vector R? We find out the direction of vector R in terms of the angle that it makes with, let us say, vector A, which is the first vector here. We call it the vector phi. So, if we are able to find out the angle phi which vector R makes with vector A, maybe we will be able to express the direction of vector R also, right. In that sense, the direction of vector R will also be specified. How do we find out the angle phi? Once again, look at the bigger right angle triangle that we have, the triangle OQS. In triangle OQS, see that we can write tan phi, tan of the angle phi, which is the opposite by the base, QS by OS, and let us then substitute the values. QS by, first thing is split OS into two parts, OS can be written as OP plus PS, and now we substitute the values. So, we get tan phi is equal to QS, which is B sin theta from the first equation that we have found, and OP is nothing but the magnitude of vector A. So, we can just write it as A, plus PS is nothing but B cos theta. So, this is the expression that gives us the value of phi, the angle that vector R makes with the first vector, vector A. If you want, you can express phi from this expression as tan inverse of B sin theta over A plus B cos theta, which is nothing but just another way of expressing the same thing, right. So, here we have got the magnitude as well as the direction of vector R, which completely specifies the vector R, right. Now, let us go back and see how we can find out the angle between any two vectors. So, finding the angle between vectors. So, the general rule is, when you try to find out the angle between two vectors, you keep them in such a way so that either their tails are coinciding with each other like this, or their heads are coinciding with each other like this. You should never have the tail of one coinciding with the head of the other when you are trying to find out the angle between them. That does not give you the correct answer for find the angle. So when you have the two vectors A and B whose tails coincide over here, and then you find out the smaller angle that they make with each other, this angle theta will then be called the angle between vectors A and B. In the same way, when you take the heads of the two vectors together, when they coincide, and then you just try to find out the smaller angle that they make with each other, this angle, this will become the angle between the vectors A and B. It is not the bigger angle that you measure here, this is not the angle to be measured, it is this smaller angle that is to be measured. Okay. Now, what happens when you have to find out the angle between vectors when the tail of one coincides with the head of the other? This is how we have been working with vectors before this. So, if we have the situation like this, the figure is like this, how do you find out the angle? This will not give you the correct value now. This is not the angle between them, because right now their tails are not coinciding. It is the head of one which is coinciding with the tail of the other. So, what you do is, either you shift one of the vectors so that either their tails coincide or their heads coincide. So, maybe you can shift the vector A little further like this. Maybe you can bring vector A over here like this, and then you can say that it is this angle which we can call as the angle between the two vectors. Or if you do not want to shift the vector as such, you just extend the vector by just drawing a dotted line in the direction of the vector itself. So, if we have the same way in which A and B are drawn, you just draw a dotted line in the direction of vector A, and now you say that this is the angle between the vectors A and B. So, instead of actually shifting the vector A, you have just extended that direction to see what is the angle between the two vectors, and see that it is this particular method that we have used in the above expression, in the above exercise that we did to find out the angle between the vectors A and B. So, this angle theta essentially we have obtained by extending vector A forward, right. So, please keep this in mind that the angle theta between the two vectors has to be measured in this particular way. Now, once we have got this expression for the resultant, it would be good if we can just take up a few special cases associated with the resultant value. Some special cases. The first case that we shall take will be the one that when the two vectors are parallel to each other, vector A is parallel to vector B. The two vectors being parallel means that the angle that they make with each other will be 0 degrees. Understand that the two vectors will look like this. This is vector A, and in the same direction we will have the vector B, right. So, I hope you all understand that the angle that the two vectors make with each other here will be 0 degrees, right. Now, in this case, what will be the value of the resultant R from the above expression? The above expression is R is equal to square root of A squared plus B squared plus 2AB cos theta. Theta is 0 degrees, so I will just write cos 0 here instead of theta. Cos 0 we know is 1. So, this will become A squared plus B squared plus 2AB, that is it, cos 0 is 1. And this is nothing but the formula for A plus B whole square, which will cancel out with the square root to give you A plus B, that is equal to R. So, this is an important expression. This tells us that the magnitude of the resultant is equal to the sum of the magnitudes of the two original vectors. Yes. So, it is in this particular special case when the two vectors are in the same line, they are along the same direction, that you get this expression to be true. And if we try to look at the figure here, if A and B are two vectors parallel to each other, the resultant will be like this. It will be the sum of the two vectors, which you can look at from the figure itself. We understand that the length of vector R will be equal to the length of vectors A and B, which is basically this expression that we have written. Yes. Second special case will be when vectors A and B are in the opposite direction. Vector A is anti-parallel to vector B, which basically means that the angle between the two vectors now will be 180 degrees. Do we understand this? Vector A is like this and vector B is like this, So when we try to find out the angle between them, it will be this angle, 180 degrees, isn't it? So in this case, we try to find out the value of r, the resultant, magnitude of the resultant. It will be a squared plus b squared plus 2ab into cos of 180. Cos 180 is minus 1. So this will become a squared plus b squared minus 2ab, which is nothing but the square of a minus b. A minus b whole squared, and this cancels out with the square root to give you mod of a minus b as the value of r. What is the meaning of this modulus sign here? The modulus sign means that the value of a minus b, the value of r will be a minus b if a is greater than b. It will be a minus b if a is greater than b, magnitude of vector a is greater than magnitude of vector b, and it will be b minus a if b is greater than a, which basically means that this quantity that you get should be a positive value. The magnitude of a vector can never be negative, a length can never be negative. So you should always take a positive value, and accordingly you have to change this expression. Yes. So if we try to look at this the resultant vector through a figure, it will look like this. Let's say we have this as our vector A, and if we try to draw vector B which is pointing in the opposite direction, I can draw it like this, which is, let's say, smaller than vector A. And then when you try to draw vector R joining the tail of A with the head of B, this will be your vector R. From the figure you understand that it is indeed true that the length of vector R will be equal to the difference of the lengths of vector A and vector B. Yes, which is what is given to us by this expression. The third special case that we can take here is when vector A is perpendicular to vector B. If the two vectors are perpendicular, that means the angle between them will be 90 degrees. Do we understand this? If vector A is like this and vector B is just perpendicular to it, like this, do we see that the angle between them will be 90 degrees? So in this case, what will be the value of r? R will be square root of a squared plus b squared plus 2ab cos 90, and cos 90 we know is 0. So the third term will go to 0 and will be just left with square root of a squared plus b squared, which is r, and this can also be written as r squared is equal to a squared plus b squared, which is nothing but an expression similar to the Pythagoras theorem. We understand this from the figure also. As the two vectors are drawn perpendicular to each other, see that the resultant will come like this. This will be the resultant vector. Look at the figure carefully and understand that the three vectors together are making a right angle triangle, where the resultant r is the hypotenuse and the two other vectors, original vectors, are the two sides, and indeed the Pythagoras theorem will then be valid among them, isn't it?